So vocabulary for this unit: nebula, cloud of gas and dust; density, you'd always be surprised how many people don't know density; atmosphere, the collection of gases surrounding a planet, moon, or star. Now here's the thing, notice that it does not say oxygen. You do not have to have oxygen to have an atmosphere. And finally, geologic time, basically the breakdown of Earth's history separated into whatever humans decided is the eras, epochs, and periods. Now for the age of the Earth, the solar system, about 4.55 billion years old. Our oldest rocks on Earth, only about 4.2 billion years old, because, erosion has destroyed them. Plate tectonics have destroyed rocks. Asteroid impacts destroys rocks. Plants, chemical weathering, a lot of things on Earth destroy rocks. So our oldest rocks are not as old as the Earth. And even the moon rocks, when we went to the moon, grabbed a bunch of rocks, brought them back, figured out how old they were, those rocks only came back at 4.45 billion years old. So what's going on here? Why is the moon and the Earth seem like it's younger than the rest of the solar system? Well, obviously on Earth it's erosion, but the moon formed after the solar system had already formed. So we'll talk about that in a minute here. The moon came after the Earth. Now, for our solar system, where did it come from? Well, as somebody said earlier, nebular theory, it came from a nebula. All the planets and the sun formed at the same time from a cloud of gas and dust. And it kind of makes sense. If you've got just swirling, chaotic, random cloud of gas and dust, you're not going to neatly form the planets in an order. You're not going to form the sun, and then Mercury, and then Venus, and then the Earth, and then Mars, then Jupiter, then Saturn, then Uranus, then Neptune, and then Pluto. No. They're all going to happen all at the same time. Gas coming together, rocks slamming into each other. It's not neat and ordered when it comes to nebular theory. And here's another thing too. It probably wasn't just the planets you see here. It was probably a whole bunch of other planets that some of them ran into the sun, some of them crashed into other planets, some of them got flung out of the solar system. They actually think that Jupiter may have destroyed a planet just by flying it out of the solar system, or I guess not destroyed, but got rid of a planet out of our solar system just based on its large amount of gravity. And here's the thing too, the planets in this order probably weren't in this order either. Jupiter may have moved. Saturn may have moved as well. Mercury may have not been the first planet from the sun. So the early solar system was a crazy place. Now, how do we know that solar systems come from nebula? We can see it, not in our own solar system, but in other solar systems. As gravity pulls the nebula in, it starts spinning faster and faster and faster. And if you were on your spinny chair and you pull your arms and legs in, if you want to go ahead and try it right now, go ahead. You will spin faster if you pull everything in and slower if you push everything out. And so what happens was our solar system, when it was a giant nebula, was spinning pretty slowly. But as gravity pulled it closer together, it sped up and sped up and sped up. And now, right now, all the planets are going around the sun, right? They're going around because that's that leftover angular momentum from when it was a nebula. Now, collapses, how long did it take to actually go from nebula to solar system? Probably only about 10 million years. It didn't take that long. Well, I mean, for a human time scale, 10 million years is an incredibly long amount of time. But for the Earth's time scale or the sun's time scale, 10 million years is a really, really short amount of time. Now, so what happened is, if you know anything about the inner planets, is they are smaller than the outer planets. But another thing is they're also closer to the sun. And because the inner planets are closer to the sun, they get bombarded with more solar wind, more solar flares, more solar storms. And in the early history of the solar system, the early inner planets, all of their atmospheres got completely destroyed. Like when I say destroyed, they got blown out away from the planet. So Earth was left with just a barren, rocky planet. Mars, same thing. Venus, same thing. All of those inner planets were left barren. There was no atmosphere left on them. All the hydrogen and helium was gone. Now, sure, there was probably some other elements hanging out, but for the most part, we were basically Mars, what Mars is right now. A tiny wisp of an atmosphere hanging onto a rocky planet. Now, what about the outer planets? What about Jupiter, Saturn, all of them? Well, here's the thing. They are farther away from the sun, which means they get hit with less solar radiation and less solar wind. So the farther out planets, they're lower temperature, they're farther away from the sun, and so they could hold on to their hydrogen and helium. So the reason Jupiter is mostly hydrogen and helium was, well, it never lost it in the first place, and it only gained more and more and more hydrogen and helium over time. And that's why the outer planets are gas giants and the inner planets are rocky. Well, we weren't always completely rocky. We just lost that hydrogen and helium. And it's a good thing, too. If Earth didn't lose its hydrogen and helium when the sun first formed, we probably wouldn't have life on Earth right now. We'd have a super thick atmosphere that would probably be not conducive for life. It would probably be way too hot as well. So that's something that I guess is a good thing that happened. And you can see that here. This isn't our solar system. This is a different solar system. Here's the star in the center of the solar system. And you can see in this inside edge right here, you can see this cloud of gas and dust being pushed out by the star. And once it reaches this point, this edge right here, that's when it can start to turn back into, not being pushed away by the solar wind. So this is where your gas giants have formed outside of this outer edge, and your rocky planets have formed on this inner edge. Now, composition of the Earth. On the left here, the relative abundance of elements on the whole Earth. So if you took the entire Earth, core, mantle, crust, everything, put it together, what is the Earth made of? Mostly iron, oxygen, silicon, magnesium, and nickel. But the stuff that we can see, the stuff on the crust, the everyday stuff, is mostly oxygen, silicon, aluminum, and a little bit of iron. So wait a second. If the Earth is mostly 35% iron, but the crust is only 6%, what happened right here? Iron is more dense than oxygen. Clearly, iron is more dense than oxygen. Otherwise, you would see like floating iron up in the air right now. No, you don't. So the iron sunk in a liquid Earth. And when I say liquid Earth, here's what I mean. The outside edge of the Earth was liquid. Because it was being heated up by asteroid impacts, collisions, the early sun, a whole bunch of things were heating it up. It was basically a magma ocean over the entire Earth. And so what happened was, well, if everything's a liquid, if the iron's a liquid, the nickel's a liquid, the silicon's a liquid, everything's liquid, well, the denser liquids are going to sink, the lighter liquids are going to float. Let's talk about this. So the Haydenian is the first eon in Earth's history. It is from about 4.5 billion years old to about 4 billion years ago. And during this time period, basically Earth was just molten, extremely hot, metals sinking to the core, Earth's crusts cooling, becoming a little bit colder, becoming solid. But then during this eon, something happened to the Earth, and it was the moon. And then during this impact, you look 4.2 minutes, 8.4 minutes, 125 minutes. In the span of about 2 hours, Earth went from not having a moon to having a moon, but also being completely melted. You can see this red ring around here means melted. And so it remelted the Earth in the span of about 2 hours. That's quite a bit of, chaos going on. Now, another thing is you'll notice that not only did part of this early planet that hit the Earth become part of the Earth. I mean, look at this. Some of the stuff fell back down the Earth. But part of the Earth also became part of this new moon. So it's not just, okay, this thing hit Earth, then became the moon. No, no, no. This thing hit the Earth, they mixed together, and then part of the Earth became the moon, part of that thing became the Earth, and part of that thing became the moon. So everything just got mixed together in this process. And that's why when we look at moon rocks, they share a lot of the similarities to Earth rocks as well. Now, 3 major things hit or heated up the Earth. 1, collisions. Obviously, we saw with the moon. When the moon hit the Earth, that heated up the Earth. But it's not just giant planets running into Earth that heated it up. Collisions with asteroids heat up the Earth as well. And you can see this, relatively recently with the Russian asteroid that happened quite a few years ago now. When asteroids enter Earth's atmosphere, they heat up. They're moving really, really fast, and gravity speeds them up even more. And all that energy has to go somewhere, and it goes into heat. The other thing that heated up the early Earth was compression. If you have a bicycle compressor or a car compressor and you run it, if you feel that compressor, it's hot. When you compress things, they heat up. And finally, third and least of the 3 is radioactivity of elements. You might think, well, wow, shouldn't radiation give off a lot more heat? No, not really. Not as much as collisions and compression. Now, of these 3, the only one that's still going on today is really radioactivity. Compression, not so much, and collisions, really, there aren't that many So radioactive is the only one left that's still heating up the Earth today. The Earth's gravity cannot hold on to these light gases, and they got blown away. You can see this today with like Mars. Mars has a really thin atmosphere, and it gets blown away. And even you can see this on Earth. So down there at the bottom, Earth loses 250 tons of hydrogen every single day and 4 tons of helium. So let me talk about that for a second. If you take a helium balloon and you pop it, every single atom of that helium is going to go flying up into the outer reaches of Earth's atmosphere. The sunlight is going to hit it and it's going to get blown into a space. So if you pop a balloon, you can kiss that helium goodbye. It's leaving the Earth. A lot of the gases were trapped inside the Earth, and all it took was a bunch of heat and eruptions for those gases to come out of the Earth. And it's still happening today. Volcanoes still release gases even to this day, 4 billion years later. So volcanoes, they had some gas inside them, inside the mantle, inside the crust, inside the core. And those gases were probably pretty similar to what you see in a modern volcano today. Now, it was thought, and actually, yeah, it was thought for a time that comets brought water to the Earth, but isotope testing has kind of shown that no, most of our water didn't come from comets. Most of the water was actually trapped inside the Earth, and it was released by volcanoes. So here are some gases released by volcanoes, and these are what volcanoes would release even now. Mostly carbon dioxide, the stuff you breathe out, and carbon monoxide. Some ammonia, some sulfur dioxide, hydrogen sulfide, methane, natural gas, water. Volcanoes do release water, nitrogen, and you'll notice that something is missing, oxygen. So yeah, no, there was no oxygen when Earth first formed. There was no oxygen even after the secondary atmosphere came into play. For the first billion years of Earth's history, just nothing, no oxygen. There's other gases, there's carbon dioxide. Earth had an atmosphere, it just wasn't what we have right now. So for the first Haydenian, the first 500 million years, yeah, there might have been like 1 to 2%, not even that, probably about 1% of oxygen. And that's just because, ozone, when you break it up, it makes oxygen and then it reforms back into ozone. So don't get me wrong, there probably was some oxygen, but ridiculously low levels, it wouldn't even matter. Just kind of like how Mars probably has some oxygen, but it's so ridiculously low, why does it even matter? It wasn't until the Archean Eon, so you can see right there, it's in red, 4 billion to 2.5 billion years ago. During that eon, bacteria started doing photosynthesis. CO2 plus H2O plus sunlight makes oxygen and some sugars. So for the first 1.1 billion years, pretty much no oxygen. And then starting 3.4 billion years ago, now oxygen is starting to be formed during the Archean Eon. It takes time, though. It takes a lot of time. Now, before we move on too much, with geologic time, you've heard me say eons. Eons are the largest chunk of time. We're talking billions to at least hundreds of millions of years comprise an eon. You can separate eons further into things called eras. Eras, somewhere around 60 to 100 so million years for every era. You can separate eras further into periods. So periods are smaller, eras bigger, eons biggest. Periods, somewhere around 20 million years usually for a period. And then you could separate periods further into epochs, which are, around 10,000s to thousands of years long. Now, when we say eons, there are 4 eons for Earth's history. The first 3 eons are combined to be called the Precambrian. Now, the reason for that is the first 3 eons comprise the first 4 billion years of Earth's history. And for the first 4 billion years of Earth's history, not really much happened. Earth cooled down, some rocks happened, plate tectonics happened, but there wasn't really life that was very complex. You had bacteria mostly for the first 4 billion years. So it wasn't until after the Precambrian that really interesting things happened with life. And for that reason, we lump these 3 together and call them the Precambrian. And they make up about 90% of Earth's history. For 90% of Earth, at least for as far as life concerned, not much is going on. You have bacteria, you start getting, complex life forming at the end of the Proterozoic right here, but for the most part, there's just nothing. No fossils that exist from this era, no complex life, no trees, no plants, no insects, just rock history. So rock history is great, but we don't have much fossil history from any of these 3. That isn't until the Phanerozoic eon. So right here, eon, largest chunks of time, Phanerozoic. Phanerozoic is about 550 million years of geologic time. And you can see the Phanerozoic is broken into eras. So this is an eon. It's broken into 3 eras: Cenozoic, Mesozoic, and Paleozoic. So if you want to, you don't have to write those down, but if you want to, you can. You can think of as Cenozoic is like the era of mammals, era of dinosaurs, era of ocean life, but you don't have to write that down or anything. And you can see eras are broken further down into periods, lots of those, and then periods can be broken down into epochs. And we have today.